When astronomers look at distant stars and galaxies, they are able to identify the atoms and molecules that are there because they see the familiar spectral lines that are the signature of these atoms and molecules. But what they find is that the lines are not in exactly the right place, that they are shifted slightly towards the red end of the spectrum in what is known as redshift, and we understand this to be the same frequency shift that occurred for sound when the source is moving away from us. This time it's for light, that the light's frequency moves to a lower value because it is moving away. And we find that things that are further away, which could mean further back in time, are also moving away from us even faster. They are even more red-shifted. And so we have this notion of a universe that is expanding outwards in all directions where we look. Almost everywhere we look, we see this redshift, so everything is moving away from us. We think that everything is moving away from everywhere else in the universe, that it's all expanding, and so you play the tape backwards, and what we do find is that the universe then must contract back to a point-like place where it began the expansion in what is known as the Big Bang. This is not an explosion. This name actually was given to it in derision by somebody who didn't like the theory, and it stuck. But it's not an explosion of material being thrown into empty space. Rather, it is an increasing in the volume in which space exists. There is this bubble of reality within which all the matter and space and time exist. And that bubble of reality is getting bigger. That the space inside is getting bigger, but it's not like something that it's exploding outwards and being thrown into the space around it. There is no space around it. Another consequence of this understanding is that there is no edge. There's no place you could go where if you were at the edge you could look one way and see nothing, and look the other way and see the universe. That everywhere you go, you see the universe all around you, and it looks the same. There is no edge because all reality is within the universe, and everywhere you look within the universe you see reality. That sometimes we say that there is no center to the universe, but you could say that everywhere is the center, because everywhere is located at the place where the Big Bang happened. Very hard to wrap your brain around it, but fight the urge to think of an explosion. Instead, it is this bubble in which all reality exists. Dimensionality, substance, and time. And the space in which it exists is getting bigger. The volume is getting bigger. Again, I repeat. Now, gravity, because there's mass, gravity does act to try to pull the universe back together, while at the same time the universe is expanding. And so there's a conflict between those two. Again, I'm fighting to get you to not think of it as an explosion and matter being thrown apart, but instead that the space within is getting bigger. That there is this continual creation of new space. That every little bit of the universe is giving birth to new space. And so as a consequence, oh, come on now. Here's a little metric. And here are some locations in space. But if how far apart are those two places? and the same distance between those two places. But as every little bit of matter in here expands, matter of space, there become more bits of space, and each one of those is giving rise to new space, and so it makes sense that the rate of acceleration would be expanding, and that the further away you looked, the more space there would be between you, so the exponential rate at which space was giving birth to space would lead to this sense of things far away accelerating faster than things close up. I don't know if that's a real useful idea, but it's one that I am struggling with. That it is indeed the case that the universe is accelerating in its expansion. And don't pay attention to this second sentence. We'll talk about that when the time comes. If there is sufficient matter, and hence sufficient gravity, then the expansion can be stopped, and the universe will collapse. We say that the universe has a closed space curvature, and this is called the density constant of the universe. If the density constant is bigger than 1, then there's enough mass in the universe relative to volume that the gravity would cause it to stop expanding and fall back, to be closed. But if that was the case, it would have happened a long time ago. If there's insufficient matter, then there's the rate at which space is increasing itself exceeds the ability of gravity to slow it down, in which case the universe blows up. We say it has an open space curvature, usually represented by a hyperbola. That doesn't really work for me. But if that was the case, space would have blown up a long time ago. It would have gotten so spread out that we have what is called heat death. There's not enough energy around to make anything happen. That our universe exists between these two extremes with a density constant of exactly 1. We say that the universe is perfectly flat. Think about blowing this ball up, and the sense of curvature would go away as it got bigger and bigger. It would become to feel flatter and flatter locally. Well, so maybe from that you move to flat, but then if you move beyond flat, that this density constant go down to 1, and then it goes below 1, then this flat surface sort of flips around and bends into this hyperbola, which is supposed to be the opposite of this closed surface. I'm certain that that's a bad idea. Well, if there was too much matter or too little matter, the universe would have gone away a long time ago. But the universe is here, so we know that it is almost perfectly flat. That if this constant here differed from being exactly 1 in the 60th decimal place, then one of these bad boy scenarios would have happened. It is so amazingly flat. So the question is, how did it get that way? And one argument would be, well, if it wasn't that way, then it would have died a long time ago, so maybe the universe just keeps trying over and over again, and we got lucky, and all the bad luck tries at making a universe are gone away. But we move on. Okay. Now this image is the one I want you to understand what it is saying. And so I'm going to go through this in detail, and I want you to be able to give meaning to this picture. Please note that from the Big Bang on, we have time along this axis, and it is definitely not linear time. What a chunk of time means here is going up exponentially, crazy exponentially. And along this edge here we have the temperatures, which again is a linear scale, but the temperature does keep dropping as time goes on. Okay, The first era here is called the Planck era, like Max Planck, like the guy we studied when we studied quantum. That in this era here, there is so much energy around that everything, all bosons and fermions and mesons and gauge bosons, all of them seem to have unlimited lifetimes. You know, we recall that when most of them had rather short half-lives, and the more massive they were, the shorter their half-life was. Well, that was a part of the fact that to be very massive was to be very energetic, and then you had the Heisenberg uncertainty, and so you had to borrow a lot of energy, which meant you could only live for a short amount of time. Well, it is so extremely hot in here that there is so much energy around that everything seems to have an unlimited lifetime, and you can't tell the particle, well, unlimited up to 10 to the minus 43 seconds. But everything is indistinguishable. We say there is a symmetry, and you can't distinguish between the particle that carries strong nuclear force and a proton. They all look the same. The other thing that is true all the way up to here is that quarks exist freely, not in quark triples or quark pairs, as we understand must be the case, but in here, evidently, they could exist freely. I don't understand that. And then we get to this end here, and each one of these borders is going to be a symmetry breaking. And in this case, it is gravity that starts looking different than the other forces and the other stuff. And so gravity differentiates, and that is what happens at this point. And then we enter the GOOT era. GOOT stands for Grand Unified Theory. And it continues to be the case that because of the high temperature, you cannot tell the gauge bosons, the gluons, which do strong nuclear force, and the Ws, which do the weak nuclear force, and the photons that do electromagnetic force. You can't tell them apart in here. They have unlimited half-lives, and they are indistinguishable from one another. So we say there is symmetry. But at the end of the GOOT era, there is again a symmetry breaking, and strong force differentiates from the other forces. This is also the point where inflation occurs. And let's talk a little bit about inflation. The idea is, how do we explain the universe being as flat as it is? And somebody proposed that, well, maybe the universe suddenly blew up very fast. It was expanding very rapidly, but what about if the expansion just went crazy? Instead of going up by a factor of 1,000, we're going up by 10 to the 35. And if that happened very quickly, and the idea is it happened very, very quickly, that what you end up with is a universe that feels very, very flat. There's another problem with why the universe is so uniform. And according to physicists, for me to be the same as you means that I have to know about you, or I can't be the same. And so the problem is that there are parts of the universe that are more than further apart than the distance that light can travel in the life of the universe. And so how can they be the same? They're too far apart to talk to each other. And the idea is, no, once upon a time, the universe was very close, and the distance that light could travel, that information could travel, meant that this part of the universe knew what this part of the universe over here was like. And so they all became very similar, and could know that they were very similar. And then the universe goes crazy and blows up like this, and that means that while parts are further apart than they could know about each other, they could still be the same. I don't know if you found that interesting or not. Now we enter the hadron era, and I hope that has meaning for you. A hadron is one of those things with 3 quarks. That in fact, what happened here, this symmetry breaking, we ended up with the gluons, or the source of strong nuclear force, differentiating, and gluons hold quarks together. And so we end up with these quark triples and quark-antiquark pairs, which are the baryons and mesons that make up the hadrons, stuff made of quarks. So free quarks is over in this era here. Things continue to cool down until then you have the boson that does the weak nuclear force, the W boson. Also, there's a symmetry breaking, and we get the W boson coming free. But a W boson, at these cold temperatures here, a W boson does not exist forever, and W bosons decay very quickly into an electron and an anti-electron neutrino. W's also decay into positrons and electron neutrinos, that is anti-electrons. But these things, electrons and neutrinos, I hope you remember, were called leptons. And so we call this the lepton era. And this is the first time when we have these leptons dominating what's going on. Here, hadrons are dominating. Here, the forces are dominating. At the end of this era, things get sufficiently cold that not really a symmetry breaking, but one of the more dramatic events. Up until here, there has been sufficient energy around that matter is created from thermal fluctuations. Out of the energy, matter and antimatter spontaneously arise, but then matter and antimatter combine with one another, they annihilate one another, and they give off a gamma photon. They give off energy. And so up to here, there has been a kind of a symmetry between matter being created and matter being destroyed. But at this point, the temperature gets sufficiently low that these thermal fluctuations are not able to continue to create matter, and this process here dominates. And all the matter and antimatter in the universe at this transition here annihilate one another and go away, giving off photons, and so this is called the radiation era, when photons are dominating the universe and the matter is gone away. Well, not all the matter. Fortunately, when all the matter and antimatter annihilated one another, there was a slight excess of matter, and physicists worry mightily about why there wouldn't be exactly as much of both of them. But we're lucky that there was, because we exist. And that little smidgen of extra matter that was around and didn't get annihilated is what makes up everything in the universe today. Now, during this period here, I think I'm supposed to go on to the next slide. During this period here, where photons are dominating in the radiation era, while they dominate, they still keep running into that small smidgen of matter that is around, the electrons, the leptons, and the protons, the hadrons, that are here, keep getting in the way. And every time a photon tries to go someplace, it runs into an electron or a photon. And so they do not go freely. We say the universe is opaque. Light does not travel through it because it keeps running into stuff. Also, in the course of this era here, the radiation era, there is something called nucleosynthesis. That is the creation of nuclei. That specifically that would be helium nuclei with 2 protons and 2 neutrons. They would also make deuterium, which is a proton and a neutron in that region. But at this point, all of these protons are made, and that is the way the universe has been ever since. That at that point, they can work out theoretically that there would be this split of 85% of what's made would be hydrogen, 15% would be helium. And if you look around the universe today, if you look at the gas giants, the Jupiter and Saturn and Neptune and Uranus, you find that they are essentially 85% hydrogen and 15% helium. If you look at our sun or any other star, you will find it is essentially 85% hydrogen and 15% helium. All of that left over from that event. Now, all the other matter, there was a smidgen of lithium, but all the other matter in the universe, all the other matter of the periodic table, was made in stars. But that hydrogen, helium, and a smidgen of lithium was made at this point here. They're made in the other elements are made in the stars through fusion and through a process called neutron capture. That if you're interested in, you ought to take astronomy. Okay, so here we've got this opaque universe, and then at the end of that period, the temperature has gotten sufficiently cool, mainly because of the universe expanding, it has gotten cool. After all, it can't radiate its heat away. It is the heat, so it's definitely the universe expanding led to this cooling, and things get sufficiently cool at this point that the photons hitting electrons stop knocking them off of their attempt to bond with the protons. That is, atoms form. That is, nuclei with electrons around them. And that pulls the electrons out of the way, and for the first time, photons sail freely. We say the universe has become transparent. This is spoken of as first light, and you will see a picture on the next page of that light from 3,800,000 years after the Big Bang, after this event. That's when light first exists. That is the furthest back we can look, is to that point there when light first started moving freely through the universe. And it is in this era here that all the stars and galaxies are made. We'll talk more about dark energy in just a minute. This is the picture of that first light. It's called the cosmic microwave background. And it starts out at light that is extremely hot. What was it? 3,000 K? That is gamma ray hot. But since that time, over the roughly 14 billion years since that time, the universe has continued to expand, and so those very short wavelengths of this gamma radiation have been stretched as the space in which they exist has gotten bigger, and now they are relatively long wavelengths, centimeters in length, and they correspond to 3 Kelvin in temperature, which is pretty cold. And that is the temperature of our universe. But what astronomers are most amazed by is how uniform the universe is. This may not look very uniform to you, but these difference in colors represent changes of less than 1 part in 100,000. That it is very small differences in temperature that is represented by these, that the universe is remarkably uniform. Okay, and then to the last bit here. In the struggle to understand how the universe is as flat as it is, they invented this inflation idea. But they have also invented other exotics, that to understand why the galaxies spin as fast as they do, that requires centripetal force, and there wasn't enough gravity to make enough centripetal force, so astronomers invented something called dark matter. That is, there must be more matter, more source of gravity, but we don't know what it is. But that is not enough to explain the flatness of the universe. So astronomers have had to invent another material that's different than dark matter that they call dark energy, which is also a source of mass and makes up enough mass to make the universe be flat. We have no idea what dark energy is. 23% of the matter in the universe is thought to be this dark matter. Another 73% of the source of gravity, call it matter if you like, of the universe is this stuff. That adds up to 96. Only 4% of the source of gravity of the mass of the universe is baryonic matter, the kind of stuff that you and I think is everything, that makes up us and our world and the stars and everything. We thought this was reality, but it turns out we don't know about 96% of reality. In looking backwards, that slide I told you not to pay attention to earlier, astronomers have found that this accelerating universe, which is accelerating because as space generates more space, then there's more space to generate space in, and so it accelerates, but the rate of acceleration has increased in the last half of the universe's life. Remember, this is nonlinear, that up to here, from the Big Bang to this dotted line, is about 7 billion years, and from there to there is about 7 billion years. And this is called the dark energy era. We feel like dark energy is the reason why the expansion is increasing, that somehow dark energy seems to be pushing stuff apart. So that's how weird the Big Bang is. Thank you very much.